And we're back. Hello, everyone. Welcome to another episode of Profiles in Risk. I am your host for this episode, Nick Lamparelli, and it is cold in Florida, 60 degrees. I'm all bundled up and trying to stay warm. And today we're going to be talking about catastrophes. We're going to be talking about flood. We're going to be talking about modeling. And I'm very pleased to introduce a friend of mine now, Danny. Yasu, Danny.
Yasunik. I mean, it's even colder here in Zurich.
It's probably colder in just about anywhere than here, but once you
Yeah.
move to the warmer climate, you become a big baby. And so, yeah, now I'm inside, even though it's air conditioned, I'm still like, oh, it's cold out. I need to wear a jacket. Very strange. Danny, we start all of these episodes by allowing our guest a little time to do an elevator pitch and discuss themselves. So you are Hellenic of background. Why don't you tell everyone what your real name is? I won't even bother trying to pronounce your last name. I'm gonna have to copy and paste that into the show notes anyways. But Danny, who are you and who is Reor 20?
Thank you, Nick. My name is Danny Chatziprodromou. But even my mom was calling me Danny since I was born. Last name always a problem since I left Greece. A lot of jokes here in Switzerland for about my last name, but yeah, I was born and raised in Greece. I became an engineer and then moved to Switzerland for my doctorate in computational fluid dynamics, Technical University of Zurich. Then I sold my soul to the devil, let's say, and I did a postdoc in financial mathematics. And I started working in the finance industry right after doing quant stuff for the investment. Caused about a third of the crisis in 2008. So, and after some point, I realized that I'm not mixing very well. My personality wasn't mixing very well with the finance industry. Nothing bad against the industry, but it wasn't me. So I decided to redeem a little bit my soul, and I moved from finance to insurance, where I started working for Swiss Re, various roles in the company. Started from a very scientific role, which was evaluating emerging risks, having focus on financial and technological risks that are going to hit us in the future. And then after a couple of years in the company, everything I have done in my life up to that point magically became big data. So it had a name finally. It was big data.
Mhm.
So I took one position leading a big data and innovation team, work developing ideas, products for Swiss Re. And at some point in my corporate career, I was confronted with flood models. So imagine 5 years undergrad school diploma here in Europe. We have in Greece we have the German system, so it was 5 years diploma, and then another year in my master's, another 3 years in my postdocs, roughly 10 years in academia studying fluid dynamics, and I didn't touch my fluid dynamics knowledge up to that point in my professional, let's say, life. Suddenly I'm saying the first relevant thing to what I study in insurance, and that was flood models. Having the background, I understood why the flood models are as they are, what are the scientific reasons behind, but I was scared to my core that people were taking decisions, business decisions on this information. So nothing against the fellow scientists that build the models. I mean, they do amazing job with what the science is allowing for. But I was finding it very difficult to accept that we take business decisions on that. And I will elaborate more on that. But so that day, I'm calling my friend and now partner, Christos, another fellow Greek that was at MIT at the time. I said, Christos, can we do high fidelity modeling at large scale without breaking the bank in terms of computational power? He was like, okay, it was late here in Europe, early in US. So, are you drunk, man? We studied all our lives to know that this is not possible. So But that triggered a discussion. And the discussion brought up an idea based on, I could characterize them even science fiction type of ideas, discussions in academic cycles, predominantly in US, in MIT area, but there was no proven, let's say, idea that this might work, which is like, can an AI learn how to do physics? And based just on that and building a little bit of conviction that is possible, I took a leap of faith and I left my nice, comfortable corporate life, took my pension fund, took all my savings, 43, thinking that I know how to build a company. I was totally wrong. I mean, I didn't have a clue how to build a company, but I had all the conviction, and yeah, it takes a little bit of naiveness, let's say, to do that. And 6 years later, here we are.
Yeah, you can take the philosopher out of Greece, but you can't
Yeah.
take the grease out of the philosopher. So which is fantastic. So before jumping into this high fidelity modeling, let's back up. Let's talk about the predominance of the models that do exist, right?
Mhm.
Which are derivatives of the hurricane models that's predominantly that were developed 20 plus years ago by RMS and AIR, which if you think about 20 years ago, like computational power was different, how we handled databases, right? Like the physics probably wasn't even like fully understood. I think we're still learning about the physics, right? Can you talk about that kind of modeling, like the philosophy behind it, and maybe discuss the physical challenges, right?
Yeah.
Because you 20 years ago you could not have done what you did 6 years ago. So what needed to change? And let's give kudos to the model builders for what they built, given the technology that existed. Just walk us through a little bit of the evolution of models, but flood models as well? Like, how was it done prior, and what needed to occur for RIOR 20 to actually be able to do high fidelity modeling?
Yeah. So first of all, I cannot stress enough that how much I agree with the kudos to the people that they built the models, and they keep on building, and they're doing an excellent job. A couple of things, especially fluid dynamics is in the end, with fluid dynamics, you're doing still models. Okay. So the models are having imperfections, and a lot of the imperfections are coming also from the input data. So actually, we see a massive effort into collecting data, geospatial data, and building attributes like topographies. All that are extremely valuable to help build more accurate models, because the input is one thing. The second thing is like you touch upon it, is like computational power. Especially when those model developers started building, there was no computational power available that could handle that vast amount of data. And in order to have a flood model that is meaningful for insurance, you need to tackle a country. You cannot do a little neighborhood, because that is of no value in the end for the insurer. So actually, what they had to do, and they did it very successfully, was to find a way to water down, pun intended, the mathematics behind, in order to simplify what they had to solve, in order to accommodate the scale and still provide a meaningful number. And they very accurately managed to produce a maximum depth kind of number that is reasonably accurate. Of course, in the process, and in order to simplify further the problem, because still the computational power was not able to handle that kind of scale, they had also to remove the buildings from the calculations. So actually scraping the earth, because it's not that the building is creating any kind of difficulty for the solution. It's like the grid that you have to build underneath has to be much denser, and actually this indicates the size, and then this is propagating to the whole domain, and you have millions or billions of numbers, let's say. So it increases the complexity of what you have to solve. So actually, scraping the earth from the buildings was number one simplification. Watering down the mathematics was number two simplification. And going into calculations at 30 meters resolution was the third simplification. And also, the available data, especially when you're talking about 20 years ago, were not more granular. Even now, you struggle to find more granular information. And in that way, they managed to produce flood maps that are sort of giving a good feeling about where you are going to have the maximum depth.
Mm-hmm.
Saying that, the other problem is like cannot handle very, very fast events, meaning when we're talking about flash floods, it is still a problem even for all those simplifications. Unfortunately, computational power, yes, it is more available, but it's not enough to do high fidelity with buildings yet. So even now, you can do some smaller regions, but when you want to do a country or a county in US or whatever, that's not possible. I mean, you are going to explode the Amazon cloud. That's why what we're saying still is like more or less the models evolved. Of course, run more simulations, not only a single type of event, but still are suffering from all those factors that I mentioned.
Yeah. And I think the important nugget of insight, I think, from what you just described, I think the audience really needs to process through is that it's essentially you're discussing trade-offs. You have to make decisions. You ideally, in an ideal world, the model would accurately reflect the physical reality, but that's an impossibility because, to what resolution do you need the topography, right? 2 inches, statistically, you don't need that. Statistically, you can get to some degree where you're, 95% of the way towards something that's accurate and the other is just noise. But I think it just goes to show like the challenge that even today with these computers that we have now, you Reor 20 still has to make trade-offs.
Yeah, that's what we're trying to overcome with the new technology. Because if you go full-blown computation fluid dynamics, it's inevitable. Meaning that the computation fluid dynamics part is, there are hundreds or thousands of scientists out there that they can do that. The high fidelity computations is not a secret. You can do it. There are very smart people out there that they can produce amazing, fully high fidelity simulations. The problem is, again, if you want to go at scale, you will be blocked by a couple of factors. First, availability of data, then complexity, then still computational power not enough. So actually what we had to do was like to invent a new science, more or less. Not a new science, a new type of AI. Let's not exaggerate. The new science is a very, very big word. No, a new type of AI, an AI that can do computation fluid dynamics. So that's what we did. That's what actually are in possession of right now. And we're very happy to see that we can accelerate very complicated calculations and reduce costs by orders of magnitude. And that is giving us hope that we will be able to provide at least the computational engine to go as close as possible to reality. But again, data in is a big, big problem. The industry is working on that very intensively. And we appreciate that because we are not the company to do that. Don't come to us and say, do you have the building data or do you have that kind of data or this kind of data? There are amazing companies out there that we're working with that are providing that, and they're working on that.
Yeah. Can you talk about the challenge that's specific to flood? And so you've clearly listed a lot of the technical challenges, but there's also what the definition of flood is and like all of the various ways that it can occur. So can you go into a little bit more detail of just the challenge of having to deal with tropical, non-tropical, you brought up flash flood, like talk about like these different mechanisms, and I think it'll enlighten the audience as well as to why this specific peril is just so massively challenging to try to accurately forecast.
I think, I mean, it's a very, very big question, actually. Three main types of flood. You have the coastal one, which like practically pressure is pushing the water out. You have the riverine, which is a bit slower, a bit more predictable. And actually, the flood maps that we are accustomed to have are predominantly used developed for this kind of flood. And there are flash floods, of course, tropical floods, which can be a kind of a flash flood. So very fast floods that are happening because you have an intense rainfall somewhere and can happen actually at very dry places. And this is another thing that is
Yeah.
extremely challenging because, for example, flood maps are predominantly showing areas around water bodies that are at risk. But Utah might be a big risk area because it's dry, like it is Saudi Arabia, for example. That because they are extremely dry, then you have the rain, an intense rain, fast rain. The permeability of the ground is very low because it's like concrete everywhere, and then you have massive flood, massive catastrophes. And there are so many ways that you can be flooded. So, for example, you get Germany. Actually, the infrastructure failed at some point. You got a wave in the middle of a valley. You cannot even imagine. And 8 meters is, I don't know, in feet, 20 something feet of
Yeah, 20, 26, 27 feet.
yeah, in the middle of the valley. You get a wave. And people were sitting in their living rooms and they were suddenly they swept away because of a wave because of intense rainfall. So even to give instructions what you should do in order to be protected when you have accurate warning is very, very difficult because yes, that much of rainfall is coming towards you. What does this mean on the
Yeah.
ground? It is extremely difficult. Also, we were talking about prevention, and you build something to prevent, and then you move the problem somewhere
Yes.
else.
Yeah. Yeah.
Even the conditions of the ground at the time of the event crucial, meaning you have blocked manholes, the water doesn't go in the drainage, you have a problem. You have saturated ground, doesn't absorb, is not able to absorb more water, so it is more water is staying up. Then you have bottom up flood, so floods that are happening from the drainage out because the capacity of the drainage is not enough. You know, and in that sense, we will never solve the problem, meaning that it is so difficult to be accurate for all of these. So still, even with the perfect engine, if we assume that we build the perfect engine, it is impossible to take
Yeah.
account.
I think about Hurricane Harvey, for instance, and roughly 50 inches of rain fell in a 48-hour period in the Houston. Houston, can you imagine? It's just mind boggling. And theoretically, some of the flooding was due to changes in infrastructure. So soil that once existed that could have absorbed got covered over with concrete because I think Houston's very well known for being like a concrete jungle. And so you have the sprawling metropolis of concrete and asphalt, and there's literally no place for the water to go. So those bayous just completely fill up, and they just keep filling up like a bathtub. The water cannot discharge fast enough, and we're in some places we're creating bathtubs in these situations. But it gets to I think it's very important for the audience to, as they're listening to you, when I think most insurance professionals think about modeling. I don't think they can appreciate like what you just described. Because think about the ability for water to move. Well, it's different in the wintertime than it is in the summertime, and different in the fall. And so you have to overlay the probability of a storm hitting at a certain time of year with conditions on the ground behaving in a certain way. And really, the only way that humans have been able to computationally handle that is to just run more simulations to
Exactly.
go out, right? And I don't think most folks understand that like the traditional models, we're talking tens of thousands of years of simulations to try to catch that that one storm that comes in the winter time where the temperature is changing and you get a snow melt, but there's ice dams still in the river, and like you get this black swan event and everything just stacks on to create this massive flood. But it might be a 1 in a million year type of scenario that's occurring when you get all of the events lining up, all of the planets lining up. But that's the challenge. And so from I'm curious as not I was always curious as to how machine learning and AI would affect
Mhm.
catastrophe modeling. How did you guys go about AI has really gotten hot over the past year, right? But
Yeah.
machine learning has been around for a while. How was machine learning and AI always part of your potential business model?
Yeah,
And how
actually,
did how did you think about applying that, given that to train a computer to basically learn physics or whatever? That seems like a an endeavor above and beyond just creating a complex flood model.
yeah, actually, that is. I told you that when I started the company, the thinking was a bit naive, So meaning that we didn't have enough conviction that this is possible. It is, but it was the only solution in our head. Potentially, some people will come with other solution that we will be able to develop a solver practically that can provide, let's say, minimize the simplification needed to be done and provide the wealth of simulations need to be done, because still we are not running even a thousandth of the simulations that we need to run in order to understand.
Incredible.
So the whole idea of Rare is like, okay, can we teach AI to do physics? And we'll elaborate on that. What does this mean? And how we are thinking about it in order to be able to give momentum into the equation. Because, for example, same right now for the industry, same depth means same risk. But one property is in a waterway and the other property is on a flat. It's not the potential of the water is not the same. It is much more catastrophic when it's moving fast towards you. Everybody has been in the sea in, let's say, 1 foot of water and standing, and 1 foot of water as a wave.
Moving. Yeah.
No, it's not the same. If the
Mhm.
one is pushing you, the other is not. So, and we have many examples in different tasks that we had for insurance where we could show that they underestimate the risk because same depth is not same risk necessarily, especially in hilly areas, especially in areas where you have, especially in fast phenomena, where the potential of water might be really, really high. So regarding the AI and how we thought of that we can use it, there are several ways to go. The one thing, the most simple would be like, okay, we run enough simulations, high fidelity in one area, and we train our algorithm in this area. But then every time that you go to the next area, you need to retrain your model
Yeah.
because it's learning the characteristics, and that is not particularly scalable. It will take tens of years to train models like this. So we started playing with the idea of teaching the physical phenomena. So actually, our training sets are not real training sets, are training sets that we develop and that obey the physical laws. So momentum conservation, mass conservation, diffusion, convection, source terms. So because physics are unified around the world. The same physics applies in New York and in Zurich. It's the laws are the same. So actually, when you have an AI that understands the laws of physics, then you don't need to retrain for a new area because it is like when we're solving the Navier-Stokes equations, the fluid dynamics equations. We don't need to re-establish a set of equations when we go from the one area to the other. It's still the same equations, just the input is changing. And we're thinking exactly the same for the AI. We don't change the math, we change only the input data. And that is actually, that's the kind of an AI that we started seeing academic, let's say, publications on similar approaches on different problems. I think the first relevant publication I found was 2019, but we are existing from 2019 as a company, and we started in 2017. Mm-hmm. So, which shows how crazy it was what we tried to do. Happily enough, we're saying that what we have found in the process of developing that kind of technology is very well aligned with what is working in academia. So actually, we're in this very unique position to see academic literature coming out towards us and confirming what we have done the last years, let's say. But yeah, it is honestly, we started from a technological, how to say, aspiration, because we think that this is what is needed in order to give as much transparency as possible to the problem. And we didn't think too hard before we start, let's say.
Yeah. Well, if I can try to reinterpret and translate what you just said, because you said at the beginning, like you didn't invent new physics, but you invented a new approach. And I think that is one of the lessons I think I've been learning about AI is I think it's the speed, it's the velocity of learning that AI brings to the table. So it improves humans' abilities to learn faster because you can run simulations faster, yes, but it sounds like you trained it to learn and understand or adapt the physics in the appropriate cases, in the appropriate times, the way a human would have to make those trade-offs, except it, like you said, it would take a human years and years and years to understand and make those particular trade-offs, whereas the AI picks it up faster. So the physics isn't the same, but the adaptation of the physics for the particular, all of the thousands of use cases is the innovation around the technology.
Let me, I mean, 80% yes, I would say. So
that's good. I'll take that.
So actually, we know what is a perfect set of equations that we have to solve when we are talking about physics. Okay. Now, this set of equations, in order to solve it in a large domain, as we said, almost not possible because it's extremely expensive. So now we found a way, let's say we use AI to help us solve those equations, but the full description of the equations, no simplifications. That's the 20%. We don't do compromises there. We want the full solution because the full solution contains all the missing information. And the AI solves a system of equations not in the traditional way, which is like you do some numerical methods. They are like you have to invert some huge tables with numbers, and that is the painful part computationally. Instead of doing that, we have a solver that is based on AI. And practically the AI learn the behavior of the different terms of the differential equations, but we have no simplifications. We're providing a full two-dimensional solver. And that is so practically we didn't change the underlying equations. We didn't do any simplifications. We didn't simplify our domain. We used the full information, but we found a way to come to the result in a much faster, cheaper way. I'm talking about 100,000 times acceleration time. And just to give you an idea, when we benchmark our new technology versus the computational fluid dynamics one, we took a small domain, we ran it with a full description, as I told you, the physics-based algorithm. It cost us $700 on Amazon Cloud. And when we run it with the AI, exactly the same, with some loss of accuracy, of course. I mean, it's not 100% the accuracy. We spend $0.015.
Wow, that's significant.
That is significant. And also, the first simulation took some hours, while the other took some milliseconds. So
that is phenomenal.
yeah.
And that gets me very excited. When I hear that, because as a former flood underwriter, I recognize right away, like, we knew the models are wrong, right? So how do we protect capital in a scenario where the models are incorrect? And so, we took an ensemble approach and a very conservative approach through the entire decision tree, and that we left essentially. Bob Frady from Hazard Hub has this saying he tells me all the time. He's like, Nick, the reason why the insurance industry still exists today is because the law of large numbers. It's like, anytime something goes wrong, it's like the law of large numbers comes to the rescue. And that was the goal. The goal was to, like, we'll try to be as accurate as possible, but we know we cannot be accurate, right, in the way that someone might want to be accurate. So we'll be conservative. So we'll be inaccurate, but on the conservative side, and then we'll let the law of large numbers benefit us, and we'll get diversification, and we'll be in a much better position. The ramifications of what you described are really, really big, because, one, of course, you want to get as much accuracy as possible. But I think most importantly is, especially for a peril like flood, is can you defend against it, right? With hurricane, we know how to defend hurricane, and we know when it's coming. With flood, you may not know it's coming. You may know it's coming. And so it is having accurate forecasts around not only is it coming, but what's coming. Yeah. What could you be seeing? How do you defend against that? Becomes critically important, especially in states like where I live in Florida, where you have the predominance of the property infrastructure is right near the coast, exposed to the hurricanes, exposed to the flooding. And we could be in a situation where insurance is really expensive or difficult to get. So for, like, commercial entities, they may be stuck self-insuring. They're going to have to defend, and they're going to need to know, okay, well, how do we defend this? Should we not defend it and just tear the building down and put it up on stilts? Even if they do that, how high do we build it? There's so many ramifications outside of insurance that then end up becoming insurance problems. Can you talk about, when we first met, you did talk about defense, you did talk about risk mitigation, you did talk about being able to accurately model before and after a defense. Can you talk about the mitigation and defense and how important that's going to be, and how, honestly, the traditional flood models are really not equipped to be able to do that kind of before and after calculation?
Exactly. Up to now, we talk about, better modeling, better understanding of risk, but we didn't reduce the risk a single bit. Meaning, better model doesn't mean I can, let's say, de-risk an insurer's portfolio, but not people's risk. It's a different story. I can reduce the let's say the loss ratio of an insurer, because I can tell them, these are better risks than those risks. But in essence, the level of risk of people is exactly the same. So our aspiration is to give a solution, not just a solution for insurers, and not make people desperate because they cannot find insurance, but actually to enable people and companies to get insurance by identifying what they should do, and what, on top of that, the government should do, and even further, what the potentially the insurance-linked securities should do in order to bring money into the problem to cover for the extreme. So one of the key things that we're doing for commercial right now with a large insurer in US based is that we tell, here is the property, here is where are the biggest problem on this property, this ramp, this entrance, parking lot, the west wall or whatever. Then on the second level of information that we're giving is like where the water is coming from, how fast it's coming. So a lot of times, even the risk engineers had a different perception where the risk is coming from. So they think, for example, the water is coming from the north, while it's coming all around the building from the south. So having all this information, then we can design we're not an engineering consulting company, but with common sense, we implement some potential mitigation that is on premise, meaning a culvert there a small culvert might help the flow. If you see that kind of event from the weather forecast coming towards you, put a wall of 3 feet wall, inflatable wall in that direction. And what we can do immediately is that show all those mitigating suggestions, how they're altering the risk. So now you have the before picture, you have the after picture. Also, you can take measures that can be very, very simple. Move like chemicals from that side of the building to the other, because chemicals, it's one thing that if it starts flowing downstream, causing a lot of problems. So even reducing your environmental liability, Also, now you have an infrastructure, they implement a wall somewhere that the wall might not even be intended to be for flood protection. Recently, we've seen a case where a train track had a very, very thin wall, and that was changing significantly the flood landscape downstream. It was like to a level that is scary, and we need to call our lawyers. We cannot tell that lighthearted because people might start protesting, And it is because of this dynamic nature of risk. So actually, our big idea is that, okay, insurance is there to take the tail of the risk, maybe not the very extreme, but definitely not the average risk. The average risk is not for the insurance. The average risk is for the government. The average risk is the responsibility of the government. So actually, can we construct a society, let's say, where the government is taking their own risk by implementing efficient mitigation measures? Then the people are taking their other risk, and the companies and improve it by implementing simple modifications like the ones that are described. And then the insurance can take the rest. And for very extreme, where even the mitigation, the public, infrastructure is failing, we can very easily construct some governmental bonds that will allow the financial sector to take a bite of it. So practically, with the engine that we're developing, the data that other companies start building, we have the opportunity to build a perfect solution, which of course will have all those uncertainties, but the uncertainties that you described, but the uncertainties will be explicitly quantified, and thus interest rates, infrastructure, expenditure, or whatever can be calculated accurately.
I see living in Florida, I see particular value in especially in southern Florida, where there's so many homeowners associations, right? The municipality looking at, the ground is flat and it's basically we're building over swamp, right? So there's a lot that has to go into that. And so I think it's in the best interest of the community that's being built to forecast out accurately and say, this is how, if we're going to build here, this is the best way to build here up to some return period. We will cover ourselves. And then the fallback is, insurance and other mechanisms to get people to be whole. And to me, that's where I would love to see. That's where I just love companies like yours, because it gives us an opportunity to really tie insurance closer to the exposure, where one can influence the other, right? And insurance now, including ILS, alternative finance, has a say in how things are built, has a say in how things are rebuilt, and we can do a better job. I think the ultimately the value of insurance is not necessarily making people whole. I think the value of insurance is the pricing of risk to ultimately reduce risk. If we can
Yeah.
reduce risk, then we're creating the most amount of value possible for society.
Yeah, and to build onto that, I mean, even if you are fully insured against flood and you are a company, more than 20-25% of the cases that you suffer a catastrophic event, despite the fact that you have insurance in place, you fail to restart. So you cannot expect from the society cannot expect that the insurance is going to solve the problem alone. It is
Yeah.
everybody needs to assume their responsibilities, the risk owners to build as responsibly as possible. Of course, they need the information, and that's where we are coming in. We want to give that information. Then the government to do what they have to do. Then insurance, I'm pretty confident that they will bridge that infamous protection gap in no time. The moment that they will have quantified the uncertainties, they will be very much willing. We will find, I'm sure that depending on the strategy of each company, they will take their risk appetite. The problem is the quantification of that certainty. And yeah, the moment that you have all that, we will not leave one single person or one single company uncovered.
Yeah.
That should be the target.
Well, I want to finish this off with a final question around applications outside of flood, right? Does your technology can it improve the primary perils that we've been modeling for decades, so hurricanes specifically? But I'm thinking of the secondary perils that are Verisk just released a report that basically said secondary perils are no longer secondary. So we have flood, we have wildfire, we have
Yeah.
tornado, hail, severe thunderstorm. The secondary perils all kind of suffer from the same sort of localized phenomenon that make it create a lot of different uncertainties. So we've been modeling at a very, very high aggregate level. Does your technology hold promise for those perils as well, where we've not specifically solved for the accuracy?
So actually, what I want to say is, like, with the exception potentially of earthquake, which is a total different nature, all the perils that I have set of differential equation or partial differential equation behind, so wind, wildfires, even atmospheric pollution, I can even stretch it and say even option pricing, where we have a stochastic differential equation. All those can be tackled with approaches stemming from the one that we developed for flood. Saying that, it is not, an immediate application. So, okay, we did it for flood. It will take us 2 months to do it for wind now. But having solved the biggest problems for flood gives a clear guidance of how to tackle the rest. Now, is Reo going to do it? I'm not 100% sure, meaning that flood is the focus right now, and we want to stay there and finish with that. And when you say we want to see it resolved, that is decades in the going, So actually, we will be extremely happy to contribute with our IP and help teams or companies to build on what we develop. So, or we do it together. But that is something for the future. But yes, this is we want to believe, and we hope that we're right, that what we developed will solve eventually partially all the other problems around different perils.
Yeah. Well,
It
I
is a
lied.
transferable. It is a transferable technology. Let's say. Yeah. Sorry.
Fantastic. That's
Yeah.
fantastic. I lied. I have one more question. let's add a little wrinkle before we end this. Potential climate change, right?
Yeah.
How does that affect what it is that you're doing?
Actually, that's why one of the main reasons why we're doing it, because I mean, if you base all those scenarios that you described before only on history, you are going to fail miserably. So actually, we want to provide the industry with deep insights, checking thousands of different scenarios to understand. Again, quantification of uncertainties is key, and the climate change uncertainty is a big one because it is here. We are already into climate crisis, but how is it going to evolve? And it is unpredicted. So actually, we need to develop enough knowledge to understand how this is going to impact in the future society in general. Now, if you ask me, is that predominantly for insurance? I would say not predominantly. It's predominantly for the banks because they are giving mortgages, for example, and they are having 30 years tail. So actually, you take a risk and you hold it on your book for 30 years. Insurance is, in that sense, a little bit more flexible, but you cannot increase prices forever. You need to tackle it. So actually, it is also for the insurance. So yeah, I mean, climate change is one of the big applications of technology.
Yeah, but marvelous conversation, Danny. Thank you so much for educating us, spending a little time.
Thank you very much, Nick. I don't really think that hate anybody. I mean, I'm just sharing our experience and our effort. I hope that it will be useful for some people, and everybody is open to. I mean, I have an open door. Let's say if anybody wants to talk.
Well, we'll put your connection details in the show notes, but thank you, Danny. Yasu.
Yasu, Yasu, Nico.